Namaste, welcome back to Stithapragna channel and you are watching Machine Learning Basics Theory series, and this is the third video in this series. So far we have covered KNN algorithm and random cut forest algorithm, and in this video we are going to cover linear learner algorithm. So the first one, KNN, is supervised, random cut is unsupervised, and guess what? Linear learner algorithm is whether is it supervised or unsupervised. Yes, this is a supervised learning algorithm. Let's jump into this one. I hope you enjoyed the previous two videos. I hope you will like this one as well. And thank you for spending your time. And let's jump into this. What is linear learner algorithm? As I just said, it is a supervised learning algorithm. And by now, I think you know what is the difference between a supervised and not supervised, which is designed for linear classification and regression. Right? It works by fitting a linear model to the data, which is a mathematical model that assumes a linear relationship between the input features and the output. Remember, even the KNN is used for classification and regression, but this is used for linear classification. There we used distance, Euclidean distance. Here we are going to use a mathematical model, which we'll discuss in a minute. The linear model makes predictions by combining the input features linearly using learned weights and optionally applying a transformation. What kind of transformation? An example would be sigmoid function. I'm not going to explain this here. Google it. For classification tasks, the simplicity of linear models often makes them fast and efficient, especially on large data sets. And at the end, I will also cover what is the difference between this and KNN, correct? When would you use? Because both are supervised learning models and both are for classification and regression. We'll come there. So those are some characteristics. How linear learner works. As just like anything else, training data, the algorithm takes labeled data as in remember KNN, we don't train data. It already has data that is labeled. That's why you call it a supervised. Okay, unsupervised means you won't have data labeled. Since this and the other one is supervised, you don't label. You already give data that is labeled, or you use CNN, which kind of creates labels for you and submits the data to these models. So the algorithm takes labeled data as input, where each example is represented by a vector of features, as usual, which are independent variables, and an associated label dependent variable. We will show that when we talk about the example. For classification tasks, the labels are typically binary, either be 0 and 1, but multi-class classification is also supported. For regression tasks, the labels are continuous values. That's about the training data. And the model training, the algorithm learns, remember, learns set of weights for each feature by minimizing a loss function. Example, formula we would use is squared error for regression. Squared error, you need to remember all this. Squared error, this is for regression though. And for classification, we use logistic loss. I mean, if you are jumping into machine learning, you would have to learn all the statistics related names. These weights represent the importance of each feature in predicting the output. Okay. The algorithm uses optimization techniques like stochastic gradient descent. I'm not going to say that again. I would instead say SGD to iteratively adjust the weights to minimize the loss function. Since it learns, it has to automatically adjust and make it more appropriate or correct, right? So it uses optimization techniques like SGD to make it so that you can minimize the loss function. And then comes the prediction. Same thing, right? Any algorithm, you train it, you model it, then you do use the model to predict it. For classification or in a binary classification problem, the algorithm calculates the weighted sum of input features and applies a sigmoid, sigmoid function to produce a probability score between 0 and 1. If the score exceeds a certain threshold, for example 0.5, the instance is classified as one class, otherwise it's classified as the other. For regression, the algorithm simply outputs the weighted sum of the input features, which is the predicted value. So it doesn't classify. The extra step to classification is it uses this to do the classification and that. And two steps are not listed here, but they are regularization, which you can see here. What is this? I mean, it's not part of it. You only do it, you don't have to regularize or implement this in that particular algorithm all the time. But to prevent overfitting, the linear learner algorithm supports L1 and L2 regularizations. We have separate videos that will come later, which will specifically talk about these regularizations. These techniques penalize large weights, encouraging the model to generalize better to unseen data. You can see that L1 regulation. We will learn in more detail. For now, just know that that's the regularization. Why regularization? To prevent overfitting. And then you have hyperparameter tuning. SageMaker's linear learner can automatically perform hyperparameter optimization, such as finding the best learning rate, regularization parameters, and other hyperparameters to achieve the best performance. Okay, so I think we might have a separate video on hyperparameter tuning as well, which you will learn more about it. Now, coming to the real life example, customer churn prediction. Actually, this is what our first machine learning question is going to be on. Scenario is a telecom company wants to predict which customers are likely to cancel their service. That is called churn. What is churn? A customer likely to cancel some service. That is called as churn, based on their usage patterns, contract details, and demographics. How the linear learner is used in this situation? The company can use this algorithm to train a binary classification model on historical customer data with features like monthly usage, contract length, and age. The model predicts the probability of each customer churning, means canceling the service. And the outcome would be, by identifying at-risk customers, the company can take proactive measures such as offering special promotions or personalized services to reduce churn. Another example, house price prediction. We are going to use this scenario for our later example. A real estate company wants to predict the selling price of houses based on features like square footage, number of bedrooms, location, and year built. This algorithm is trained on historical housing data to learn the relationship between these features and the house price. The model can then predict prices for new houses. What will be the outcome? Accurate price predictions help the company set competitive prices and provide better estimates for the clients. Email spam detection. An email service provider wants to classify incoming emails as either spam or not spam based on features like the presence of certain keywords, sender information, and email formatting. You would be seeing this in real time in your Gmail, correct? Every day there will be emails automatically going into spam. So behind the scenes, they might be using linear learner algorithm. Okay, this provider can train a binary classification model using the linear learner algorithm on a labeled data set of emails. Features might include word frequency, metadata, and other textual features. And the outcome would be model filters out spam emails, improving user experience by reducing the amount of unwanted content in inboxes. Trust me, so many emails that went into my spam, if it didn't automatically do, I would have opened it. Maybe you would have as well. And then we have a final example, predictive maintenance. A manufacturing company wants to predict when machines are likely to fail based on sensor data like temperature, vibration, and runtime. This algorithm can be trained on historical maintenance and sensor data to predict the likelihood of machine failure within a certain time frame. And the outcome would be the company can schedule maintenance before failures occur, reducing downtime and saving costs. And then comes our advantages of using this one. SageMaker's linear learner is optimized for handling large data sets, making it suitable for enterprise scale applications. And linear models are computationally efficient, allowing for fast training and inference even on large data sets. The simplicity of linear models makes them easy to interpret, allowing businesses to understand how features influence predictions. And finally, L1 and L2 regularization options help prevent overfitting, making the model more robust. And considerations: the algorithm assumes a linear relationship between features and the target variable. If the true relationship is non-linear, a linear model might not capture it well, leading to lower accuracy. Since linear models can't naturally handle complex relationships, feature engineering like creating interactive terms or using polynomial features might be necessary to improve performance. All right, so that's about the theory part of it. Now let's jump into the scenario based step by step explanation of linear learner algorithm. And what is the scenario here? Suppose you work for a real estate company that wants to predict the selling price of houses based on various features such as the size of the house, number of bedrooms, number of bathrooms, location, age of the house or the year built, and more. Accurate predictions can help the company set competitive prices and provide better estimates to potential buyers and sellers. Now, what will you do? Let's understand the problem again. What are we doing here? We are predicting the selling price of a house based on its features. This is a regression problem because the target variable is continuous, which is the house price. It is going to be continuous. Now, first step is what? Remember, preparing the data. And this is a supervised algorithm, machine learning algorithm, which means you need to give data already labeled. Now we need to collect historical data on house sales, and the features might include square footage of the house, number of bedrooms, bathrooms, and the location like zip code, neighborhood, and the age of the house or year built. And another will be proximity to amenities like schools, parks, school centers, etc. Okay. And what is our target variable? The selling price of the house itself. And the next step would be applying the linear learner algorithm. Each house in this data set is represented by a vector of features. And as part of the applying the algorithm, we are training the model. Prepare the data set, correct? Data set, then train, then predict. That's all the algorithms do. Now, how do you train? The linear learner algorithm assumes there is a linear relationship between the features and the target variable. We already learned it. It tries to fit a line or a hyperplane in higher dimensions that best predicts the house price based on these features. In order for that, we said there is something called weights. Algorithm assigns weights to each feature to determine its influence on the house price. What does this mean? What does the weight mean? For example, the weight for square footage might be high, indicating the larger houses tend to have higher prices. And the year built, the lesser the year number, the less the price will be. It will be negative impact so that the weight will be less. Correct? In a linear model, the prediction is made by calculating a weighted sum of input features. What is the formula for a linear regression model? So for this particular example, the predicted price will be calculated something like W1, like weight 1 and square footage, plus W2, number of bedrooms, plus W3, location, plus W4, what is it? Year built. And it is not done yet. Then at the end you will have plus B. What is this B? B is the bias term. If you have ever linear like a straight line, what is the equation? Mx plus c, right? I hope you remember it. So this is what? It is the intercept. Same thing. Here B is the bias term or intercept. The algorithm automatically adjusts these weights during training to minimize the difference between the predicted prices and the actual prices. Correct? Because let's say it initially assumes some weight, but when it calculates, it needs to get this price based on these features, right? If it doesn't, then it will again iterate until it will get the this price based on the features and the weights. So then it will say, okay, my weights right now are the optimized one, and then it will use that weights on the price that you want to predict on a new square footage, etc. That's how this function works. I hope you, yeah, you are with me so far. Now the model starts with initial weights often. Now when the model starts, of course, it is not going to have any weights, correct? So it will assume 0 or some random values. The goal of training is to adjust these weights so that the predictions are as accurate as possible, correct? Let's assume if it starts with zeros, what will happen? All will become 0. Obviously, the price is not going to be 300, but the intercept is still there, okay? During training, the model uses optimization techniques like SGD, which we discussed, to iteratively adjust the weights. The model calculates the error between the predicted price and the actual price, and the weights are updated to reduce this error. Initially, it assumes 0, then it will value it got is not 300, then it will try to increase that value to something, and then it will try to compare is it until this one for these features it gets close to 300k. It will keep on iterating. Once it gets to 300, then it's like applies the same thing to other, and it will check, am I getting the same value for others? Then it is going to say this is going to be my weight 1, this is going to be my weight 2, etc. Correct? And then using those weights, it will apply it for the house that we want to calculate the price for. So after training, the model outputs a set of final weights that reflect the importance of each feature in predicting the house price. Okay, now let's assume the training is done, model learn the weights, and sample weights would look something like this. Weight 1, which is for the, let me scroll this here. Okay, weight 1, where did this go? Okay, weight 1 is for square foot, right? So this is per square feet, and then weight 2 will be something like 5,000. This is for per bedroom, and weight 3 is for what? Location, right? So 20,000 per location, and weight 4 is per year. So this will be 200 per year since the house was built, and then we will have the bias. Let's assume 50,000. This is the bias term. So this is same. These values are shown in this particular graph. What are you seeing here? The square footage you can see which has a positive. So this is 0. Anything on the right side is a positive. It has a positive weight indicating that larger houses tend to have higher prices. Correct? This side means higher. And number of bedrooms also has positive weight, showing that more bedrooms typically increase the house price more than the square footage. And the location has the highest positive weight, suggesting that the location is a major factor in determining house prices. Everyone will agree, right? A house in downtown will be much higher than suburbs. And year built has a negative weight, meaning that newer houses slightly decrease the predicted price in this example, or the higher year built. Now using these values, if you have to calculate the predicted price, this is how it would be. What is it? 100 times the square footage plus 5,000 times the number of bedrooms plus 2,000. You get the idea. Okay. High weights, remember, high weights indicate that the corresponding feature has a significant impact on the prediction. Low or negative weights suggest that the feature has less impact or a negative impact on the prediction. By examining the weights, you can gain insights into which features are most influential in predicting house prices. And in this instance, location score is very high, indicates that location plays a crucial role in determining house prices. And we already discussed, right? The model is trained by minimizing loss function, which is mean squared error, which measures the difference between the predicted prices and the actual prices. The algorithm adjusts the weights iteratively to reduce this error. Once the model is trained, it can be used to predict the price of new house. Okay, and let's assume that our new house that we want to calculate has square feet and 4 bedrooms and 5 years old, and the zip code, let's say 12345. Okay, now how will this calculate the value? Simple. That remember the 100 times this plus 5000 times this plus what was this? It's minus 200 times that plus I guess it's 20,000, then plus 50,000. So that's how it is going to calculate this. And this model might predict a price of 450K. Now let's look at all our actual prices and the predicted prices. Correct. So initially we have these actual prices for each one of those houses, and based on the weights it calculated, predicted with pretty much close, don't you think so? And when you plot a graph for these actuals and predicted house prices, you can see a linear model here, which is what do you line that is going like this. Equation is y equal to x. The closer the points are to this line, y equal to x, the better the model's prediction. And as you can see that pretty much all the points are closer to this line, which means the model is predicting accurately. The blue points, all you can say, represents the predicted prices for each house compared to the actual prices. And the red dashed line, which is the y equals to x, represents perfect predictions. The closer the blue points are to this line, the better the model's predictions. This graph helps visualize the performance of the linear learner model in predicting house prices. Ideally, all points should lie on the red line, indicating perfect predictions. The linear learner algorithm provides a simple yet powerful method to predict continuous values like house prices by learning a linear relationship between input features and the target variable. With this approach, businesses can make data-driven decisions such as setting competitive prices in real estate. So that's about our example. I hope you enjoyed it. I hope so. Again, as usual, don't forget to let me know in the comments if I need to improve, because this is my first time explaining machine learning concepts to anyone. Okay, so I highly, highly anticipate feedback from you, whether it is positive, negative, doesn't matter. I always take feedback and improve myself. All right, the conclusion. What is the conclusion? In the context of house price prediction or in general, the linear learner algorithm provides a straightforward and interpretable method to predict based on various features. By learning a linear relationship between the features and target variable, you can or it can efficiently predict prices for new houses in this case, helping real estate companies whatnot. But it is a powerful tool for linear classification and regressions, and it offers scalability, efficiency, and ease of use. It is ideal for scenarios where linear relationships are predominant. I did tell you that I will show, but I thought I will make a separate video on the what is the difference between this and KNN. Even though you can, some of them you can see, you will use this one um, in case of linear relationships and not, but I will provide some examples in when you will use this, when you will use that, and I will also explain the differences between two, even though both are supervised algorithms and both are used for classification and regression. All right, that's about it for this video. I hope you enjoyed it. Do let me know whether you enjoyed it or not by liking, commenting, subscribing. See you in the next video. Thank you very much. Have a great day. Peace out and love you all.